My name is Reinhard Genzel. I'm speaking tomorrow, but just now came in from Chile what I would regard as a major breakthrough. And since we're talking about breakthroughs here in this meeting, I want to show you when one happens. You are the witness of a breakthrough that happened last night. There it is. What you see there are the 4 8-meter class telescopes of the Paranal site in Chile, in the Atacama Desert. Now the experiment we're doing here is a bit the most complicated way to do optical and near-infrared astronomy ever done, namely to do what the radio astronomers do every day, interferometry. This was considered to be impossible. The only one who in the textbooks was said to do this was Michelson. But after Michelson and then Charlie Towns, this technique was considered to be impossible because of the short wavelengths, vibrations, and the fact that the technique of interferometry relies on overlapping the waves coherently to a fraction of the wavelength. And now you can do this, but the Earth's atmosphere, of course, is turbulent, and so this coherence only takes place for about a millisecond, and then it's gone. So if you want to keep it, you have to have a lot of additional electronics and so forth, which we developed over the years. And last night, we put for the first time on the interferometers, so the 4 8-meter telescopes, which act together as a telescope of 200 meters in diameter. 200 meters, not 10 meters, 200 meters. And what you see there, these red things are 4, lasers beams into the sky. What do we do with those? We shoot them into the upper atmosphere and focus them there to generate an artificial star. That makes resonant backscattering, which goes back to the telescopes. And that backscattered wave we use to correct the turbulence of the atmosphere. But now we have 4 of them, and that will improve the sensitivity of this device by a factor of probably 6. And we will now be able to do images with this device at 200 meters, so that's a milliarc-second resolution, which is better than the James Webb. So the next picture shows you, there it is, the 4 beams going up into the sky and generating these guide stars. So this is fantastic progress, I tell you. Fantastic progress, which you get to see only once every few years. And I'm very proud of the team of 5 European nations and ESO putting this together. Thank you.
Thank you very much, Professor Genzel, for the surprising speech. We look forward to listening more of your upcoming. Please be seated. Thank you very much. It's a great inspiration, and we look forward to more sharing upcoming. Good afternoon, our honorable scientists, forum participants, ladies and gentlemen. Welcome to the breakout session of astronomy. I'm Cannon Fung, your MC of this session. On behalf of the HKLF, thank you for joining us. We're extremely honored that 3 world-renowned scientists, Professor Stephen Balbus, Professor John Peacock, and Professor Michael Perryman will be sharing their groundbreaking research with us. After each of their presentations, there will be a Q&A session. To host today's seminar, in particular the Q&A session, we are very delighted to have Professor Otto Hannuksela, Assistant Professor of Department of Physics at the Chinese University of Hong Kong, to be our moderator. Without further ado, please join me in welcoming Professor Hannuksela to deliver welcome remarks and introduce today's first speaker. Professor Hannuksela, please.
Yeah. Thank you very much. So it's very nice to be here to welcome three of show laureates to share their research. So today we have three laureates. Stephen Balbus, who won the 2013 Shaw Prize for their discovery of the magnetorotational instability. And we have John Peacock, who was awarded the 2014 Shaw Prize in Astronomy for their contribution to the measurements of features in the large-scale structure used to constrain the cosmological model. And we also have Michael Perryman, the 2022 laureate, who was awarded the prize for his role in the Hipparcos and Gaia missions. And so our first speaker will be Stephen Balbus, who will be sharing with us about the background of gravitational waves and probing them with pulsars. So let's welcome Stephen Balbus.
Okay, well, it'll be a difficult act to follow after Reinhardt's amazing introduction. Congratulations on that results. Extremely impressive and very exciting. I can see right here, very good. So I'm going to break out a little bit so that I can avoid being typecast as always speaking about disks and the magnetorotational instability. I'm going to tell you about some work which is very topical, very interesting, which is a new way to detect gravitational radiation. Now, one of the world's experts is actually here in the audience, Mr. Bales, who is a pulsar person, so he will presumably keep me honest. But I wanted to talk about this because it's not, what is actually being measured is not well understood, and it's an extremely interesting and very promising way to detect gravitational waves with periods of years, even decades, which are not otherwise accessible. So let's begin half a century ago in 1974 with the first really compelling evidence for gravitational radiation. So I'm speaking, of course, of the 1974 discovery of the Hulse-Taylor pulsar, which was a binary neutron star system. One of the stars was a pulsar with a easily detected, very regular radio signal. The separation, as you see in this schematic diagram here, was almost just a little bit more than 1 solar diameter. And by comparison, the neutron stars depicted here are not quite to scale. That's 20 kilometers. That would be a pinpoint on this diagram. But what the system underwent was an evolution of its orbit by gravitational radiation. I haven't seen a video of this before. I had my student, Jake Rule, actually integrate the gravitational radiation loss equations. And it's interesting to follow the evolution. You notice that the periastron hardly moves at first. And the orbit, in addition to shrinking in semi-major axis, also becomes highly circularized. And the lifetime of the system is almost, if you follow on top, they're almost exactly 300 million years. So if we want to get a rough idea of the numbers involved here, let's say the period changes by about 6 hours in 300 million years. That makes the division easy. So that's 2 times 10 to the minus 8 hours per year, the period change per year, or 7.2 times 10 to the minus 5 seconds per year change in the period. The actual exact number is 7.6, so you can see where this comes from. About 16 microseconds per year is the predicted change in the period, and they can monitor that from the arrival times of the pulsar signal. The other star was not directly detected. It's a neutron star for which no signal was received. So it's only the pulsar that's actually seen here. And there is the actual data of the cumulative shift of the periastron as a function of time and year, and the line that's going through that is not a best fit, it's the actual prediction of relativity. So that's very compelling evidence for the existence of gravitational waves, which in the early 70s was still being argued about it being a real phenomenon or not. So that put an end to that uncertainty. So in the actual light, so to speak, of gravitational waves, before 2015, we were blind, but now we see. So here's some just recent data of various sources on the plane of the sky. The bottom and the top you don't have to pay too much attention to. One is simply in the bottom a little bit more refined techniques of localizing these sources. So the positional sensitivity is not great, but it's much better than nothing. Gravitational waves are on the air. The facilities we use are the LIGO facilities. It's an interferometric system. This is the facility in Hanford, Washington, another in Livingston, Louisiana. And then more recently, there is Virgo at, am I saying it properly? Cascina, Italy. And Kagra, the facility in Haida, Japan. So all four of these systems are in principle operational, although often one or the other of them is down for upgrading or refurbishing. So the way that these systems work, they are interferometric. You have two laser arms and a beam splitter, and in its kind of rest state, the beam splitter is a null point, and null really means null. They can count these photons by photons, so there's destructive interference. A gravitational wave comes by from above. It distorts the arm in the manner that you see here, and then even the slightest itsy-bitsy, and when I say itsy-bitsy, that's technical language for 1% of the proton radius. If you're off by, I don't even know what that means. So 1% of a proton radius, you can get a signal. And in fact, what you have is the laser beams. Those are kind of the purple signal in this schematic. And then the envelope is the gravitational wave. And you can literally read them off almost as easily as I'm depicting here. It seems to be stuck. Oh, no, I'm pushing the wrong button. Excuse me. So here's the actual data from two different facilities at Hanford and Washington with a time delay of a couple of milliseconds, as you would expect. This is the first gravitational wave source ever detected, and its unambiguous signature, it is an unambiguous signature of a merging black hole. So about 300 such events have been discovered since 2015 involving black hole mergers, neutron star black hole mergers, and even neutron star train wrecks, which is multi-messenger astronomy. Black hole mergers have perhaps the cleanest signal and have revealed a previously unknown population of progenitor massive stars. So it's not just detecting these waves, we can actually do astrophysics from what we infer from these waves. And these signals can now be deciphered with amazing precision and very efficiently using AI techniques. There is another way to find merging black holes based on their gravitational wave signatures, and it's based on the expansion and contraction of the so-called empty space due to the presence of gravitational waves and the effect that this has on any pulsar signals that may be crossing the space. This is known as the pulsar timing array. Schematically, it looks like this. There is the Earth. We see an array of pulsars. In reality, there are several hundred pulsars used. And then the distortion in the green checkerboard is meant to be a distortion in space. And in fact, it's interesting. Weak gravity and general relativity, if you're talking about static fields in the Newtonian limit, that affects primarily the time part of the four-dimensional Minkowski space. Gravitational waves in the most natural coordinates affects primarily the spatial part. So here's the way it works. There's a pulsar, which you see, and it has a very regular signal. We're talking about the millisecond pulsars here. They can be, their periods can be measured to a part in 10 to the 17. That's like knowing the age of the universe to 1 second. I mean, it's phenomenal accuracy. So the way I've set it up here, the pulsar is located at an angle theta relative to z. Z in this schematic diagram is the direction along which the gravitational wave is propagating. And if you do the arithmetic of it, the strength of the propagating gravitational wave, since it's propagating in the z direction, can be given by h of z minus zt, or it's more convenient here to write it as a function of t minus z over c. It's mathematically equivalent. And if you actually go through the arithmetic, you find that there is a slight change in the frequency. It's a bit like the way we do cosmological redshifts. The space expands and contracts, and it's given by a rather simple formula. It's the signal at the pulsar, the h of the pulsar, minus the signal of the Earth, and the geometrical factor is sine squared theta over 2. And that sine squared theta over 2 is the hallmark of a tensorial wave, which is the way that gravitational waves manifest themselves. The kind of signals that we're looking for is a relative change in frequency of the pulsar's pulses, about 1 nanosecond per year being typical. So very accurate timing is needed. The h of the Earth we can write as h of t because the z is essentially 0 here. The h of the pulsar is the time at which the gravitational wave, or the time at which the pulsar's signal left the pulsar, minus zp, the pulsar's z location over c. And tp itself, you see, has a slightly different dependence. It's t minus not zp, but r of p, the radial distance. And that's an important in terms of the way that the experiment and the observations actually work. H is typically 10 to the minus 15. That would be very large for LIGO detection, but it's very small in terms of measuring the relative timing shifts that are induced by the gravitational wave. So the idea is not take one pulsar, but to take two pulsars. And we note the P and Q coordinates for pulsar P and pulsar Q, and we apply this simple formula, but it's simple only if you can orient your axis in this convenient way, and you can't keep shifting the axis depending on which pulsars you're looking at. You have to lay it down and more or less keep it the same, so the arithmetic gets more complicated. But the idea is as you see. And what you look for is the correlation in the frequency shifts. You take the frequency shift of pulsar P, the relative frequency shift of pulsar Q, and you multiply it together. And then we're going to average it over a superposition of all the waves present. That's what the PTA measures. And the idea is that when you multiply those two things together, the pulsar's location gives sort of a random phase which averages out to 0. It's considered noise. And so the term that remains is just the h at the Earth itself times a geometric factor that looks relatively simple but gets more complicated because of the way that the spherical trigonometry comes into this problem. But the sine squared theta over 2 is very typical for these tensorial waves. So here's the problem. We have a bunch of pulsars, P and Q. There's the gamma PQ, the angle between them. And then the correlation, in theory, should depend upon sine squared gamma PQ over 2. So here's kind of an operational definition. Pick a pulsar P, measure the relative frequency shift as a function of times for many, many, many times. Draw a connecting curve. Do the same for another pulsar Q. You have two curves now. Multiply point by point the two frequency shift curves together at each time. Add everything up. In other words, integrate over time and average. Write down your result next to the angle, gamma PQ. The angle on the sky between the pulsars, that's your correlation. You're done for that pair of pulsars. Now do the same thing for all the others. N times n minus 1 over 2 pairs. You're done. You plot your correlation as a function of gamma PQ, the angle between them, and you write up your PhD. What's the theory? So that's how we do it. What do we expect? Well, the theory is based in its most basic form on two assumptions. That there is a background of gravitational waves present in the galaxy and that it's completely isotropic. That may or may not be true, but that's the working assumption for our prediction. Two, that general relativity is correct. Got to start somewhere. So we have an isotropic distribution of gravitational waves being registered on the Earth, shown schematically here. And then we have all these angles, gamma PQ, gamma UT, as I've described it. We do that for the hundreds of pulsars that are in the array all over the sky and write up what the function looks like. Where do the gravitational waves come from for this? Well, that's an open question. It's not known for sure. The most likely source of them are from the background of merging supermassive black holes at the cores of galaxies, which are common throughout the universe. If we plug in some numbers and we kind of work out what we expect the period of the gravitational wave, normally it's 2 pi for the Keplerian period, square root of a cubed over gm. A is the separation. It's only half that with the gravitational waves because it's tensorial, so it comes up twice as often in the circular orbit that I'm using here. So the period of the gravitational waves, as you can see, is about 1.5 years for two black holes, each of which are 10 to the 8 solar masses, separated by 300 Schwarzschild radius. So that's very close, but it's not close enough that we have to worry about general relativistic dynamics when we do our arithmetic. What you predict is known as the Helling-Downs curve, first derived actually in 1983, and that was done in a very different era where they were measuring trying to use the technique to measure upper limits from satellites in the solar system. So the mathematics of this is a little bit hairy. There's the integral that you wind up doing, and I can recommend an excellent textbook if you're interested to see how that's done. Soon to be sold at fine bookstores everywhere. And at the end of the day, you wind up with a delightfully simple-looking formula. You see it in front of you, 2s squared log s minus a 12th plus a third, where s is, once again, that sign of gamma PQ over 2 that's reappeared here. So what do the data show? So there's the result from July 2023 of the NanoGrav collaboration. What do you think? I think there's something. It's not the cleanest data I have ever seen in my life, but there's sort of a rise and a dip. A lot of assumptions have gone into here, but the consensus, I think, although every time I speak to somebody who's involved, there's a bit of back and forth, but I think there's a signal there. And here's kind of a more recent analysis. You see the blue dots with the error bars. I think those are 1 sigma error bars. And then the best fit is the red GA curve. Never mind with these. These are various theories of gravity. The gray shading is the 1 sigma error bars. And the black is the classic Hellings-Downs curve. So the consensus is, maybe it's stated a little bit too strongly. I'll get from the experts in the audience, I may get some feedback. I think the signal is real, the data is noisy, and the systematics are not tightly controlled. Pulsars have their own noise associated with their signals, and it has to be treated extremely carefully. The best fit curve doesn't quite fit classic Hellings-Downs. It may get better with time, it may get worse. If it gets worse, that is to say, if it doesn't fit Hellings-Downs, then that's interesting, because then we can learn some physics. One of our assumptions would be wrong. The most likely is that we're actually dominated by a few nearby sources rather than an isotropic background. Mother Nature is always full of surprises, and on this front, we've only just begun, so watch this space. And I'll stop there. Thank you.
Thank you very much, Professor Balbus. So we have time for Q&A. And I would also encourage especially young scientists to ask a lot of questions. So feel free to just raise your hand, and there will be someone to give you the microphone.
Thanks for the presentation. I know the news presented last year about the signal from like nanograph, EPTA, CPTA, IPTA. How much do you think those signals can be combined together? Well, when people try to combine signal together, the signal-to-noise ratio will increase. But how much do you think those events are independent? And how do you think those signals can be combined?
The data set certainly can be combined. And in fact, that's sort of what's sort of the meta-analysis that was done in my final slide is doing something very much along those lines. So time is on our side. Signal to noise goes down with time. And then having different arrays also look at the same data sets, and then looking for consistency, will also beat down the signal. So I think, we will get to the bottom of this, but it may take some time.
Do you think how long time we need to achieve like 5 sigma existence?
5 sigma. How about never? The pulsars are noisy. Matt, can you answer that question better than I can, perhaps, about how long? Oh, yeah.
Yeah, so I lead one of the pulsar timing arrays using the South African Meerkat telescope. Because it's a red noise process, the signal to noise should actually increase quite quickly. But these data sets are already like 15 or 20 years old. So maybe in another 5 years, you should be at that number.
Oh, that's encouraging. Good.
But the telescopes keep getting better and better, so it might even be less than that.
Thank you.
And there is something called the International Pulsar Timing Array, which is looking to collaborate across all of them. And they actually have a data combination group. And they showed an encouraging plot at the most recent IPTA workshop.
Uh-oh.
It's actually 1/10,000th of the width of a proton that the LIGO mirrors move when the gravitational wave.
Oh, I think their accuracy with the signal that they recorded was 1%.
Oh, okay.
I think their sensitivity is 100 times that. You're right. Yeah, I should be careful the way that's described. And either way, it's astonishing to me that you can measure it with these 4-kilometer long arms. Yeah. Laser interferometry is astonishing. Good.
Hey, yeah, thanks for, this is actually the first time I've understood, I think, how they actually get those results. So
you've learned something.
I appreciate the clarity.
Excellent.
You may
Thank
have
you.
already answered this and I didn't understand it, but the dominant contributor to those 1 sigma error bars that were very big, and it was hard to see, what curve fit the data best. Are those just coming from like a low number of pulsars, or those?
No.
Yep.
The pulsars themselves, their frequencies can be measured to astonishing accuracy, but we need astonishing accuracy, really, in order for this to work. So in the way Matt described it, it's kind of red noise, long period, long wavelength noise. And pulsars have that intrinsically, in addition to the systematic effect which is caused by the presence of the gravitational waves. And so you have to separate that out. And that's the difficult part.
Right.
There were skeptics that it could even be done. So it was extremely gratifying to see the 2023 results.
Yeah, you mentioned the graph from the nanograph. Is there any other observatories showing similar results of the?
Well, there's a whole consortium, yes, of groups from, I forget where, there's in Australia, in China, and India. And they're all working independently, doing independent, but also, staying in contact with each other to make sure that the signal that's being seen is consistent with these sort of independent types of analyses. So I think it's about 5 or 6 groups around the world. It's an astonishing accomplishment, the sensitivity of this, and I'm still amazed that these pulsar signals are regular to 17 significant digits, and then the residual noise can still be factored out of the process. It's a very, very impressive, undertaking. Yeah.
Right. Very good afternoon to you, Professor Balbus. Thank you so much for your very insightful and interesting presentation on this work. Really enjoyed it a lot. Thank you. And just one short question, and forgive me if it's a bit naive, but
naive questions are the best. Those are the ones I learned from. Please.
Oh, thank you. All right. So going back to the picture where you have many curves
yes.
to describe the data that you're given, this actually presents a form of model uncertainty. And I'm just wondering, moving ahead, is there any plans to develop matrix to do some form of model selection based on the data and rank the suitability?
I'm sure there are plans. I mean, since I'm not myself actually involved in the group, but there are all kinds of sort of sophisticated analyses that can be done with these sort of metadata sets to sort of pick the best sets. There's a lot of very careful thought going into the best way to make use of these independent data sets. Absolutely, yeah.
So I think we have time for one more question.
Yeah. Hi, Stephen. So the population of pulsars is anisotropic across the sky.
Yeah. Well, that's
so
right.
does that, because of the galactic plane, does that introduce any systematics into?
Well, you choose the pulsars you want to work with.
Right.
So you try and make that as kind of spherically symmetric as possible.
But if all you're considering is the angle between the pulsars,
that's right.
That you could imagine you have a bunch of pulsars towards the galactic bulge, and then less on the anti.
And of course, that's an assumption that it depends only on the angle between them.
But
right? Which would be for an isotropic background of gravitational waves. That's right.
Or I guess what I'm trying to ask is, does a population of pulsars off the galactic plane help you at all in your measurements if you were to?
Yes.
Why?
Well, if you, I mean, Matt, do you want to address that? You probably could do it better than I can.
Yeah, so the majority of the millisecond pulsars timed in these experiments are nearby, and that's because that makes them brighter. And so they actually have, there's not a huge concentration towards the galactic disk.
Yeah.
And when we were desperate, and we would just measure everything, but now we can be a bit more selective. So we actually did a census in South Africa where we looked at 180 millisecond pulsars and chose the best 90.
Yeah. It took some time to get a good sampling of having enough millisecond pulsars with well-defined periods in order to be able to do this at all. And so that's why, one of the reasons this took a while to be assembled. Yeah.
All right, let's thank Professor Balbus for the very nice talk. Thank you.
Thank you.
So it's my pleasure to welcome our next speaker, Professor John Peacock, who will be giving us a talk on convergence in cosmology. Let's welcome Professor Peacock.
Do I need to use... Okay, better. It's good job I don't need three. Is this working? Yes, that's better. Well, hello. It's a great pleasure to be back in Hong Kong after the prize ceremony in 2014. I'm very happy to have the chance to be back here. The media in recent years have been full of stories that cosmologists don't know what they're doing, that the standard model for the universe needs to be rewritten from the start. So I thought it might be interesting to give a rundown of what's behind these stories and give my perspective. So I'm going to do this in three parts, just a little bit of scene setting, then a list of the things that seem to be difficult to integrate into the standard model, and then telling you how I think it may all play out. First thing to say about cosmology is that it's a very recent enterprise. Everything we know about the universe was put into place during a single human lifetime. It all started in 1913, when Vesto Slipher measured the very first recessional velocity of a galaxy, M31. It's also the year that my father was born, so I feel a kind of personal connection to the subject. And it only took, as I said, a single human lifetime to go from knowing nothing about the universe to the standard model being in place. So let's think what we had. By 1917, Slipher had measured dozens of recessional velocities. He showed that galaxies were always redshifted, with a very few exceptions. So to me, in 1917, we already had the expansion of the universe established. We didn't need Hubble. The theory of the expanding universe was put in place in the 20s by Friedman. In the 30s, observations had shown that galaxies weren't distributed uniformly in the universe, so we had some structures, fluctuations in density that needed to be understood. The expanding universe became an observational reality in 1965 when the microwave background was detected, when you were actually seeing photons that came directly from the hot early phase of the expanding universe. The physics of nuclear reactions in that fireball were worked out in the 70s. And interestingly, we concluded that the matter in the universe, if it was ordinary matter, had to be a very low density. You'll see a lot of omegas. Omega of 1 means there's enough density in the universe to cause space to be curved enough for the universe to be closed. But around about 1980, we were suddenly told we had to think about non-baryonic dark matter, because there were announcements that the neutrino had a mass of around 10 electron volts, and that would be neutrino dark matter that would dominate the mass density. That all turned out to be an incorrect experiment, but very thought-provoking. And in 1982, Jim Peebles proposed cold dark matter as a new unknown form of elementary particle that made the dark matter. And by 1984, fluctuations in such a universe had been calculated ab initio. So we then had to wait 20 years, roughly, and then this magnificent picture of a primordial structure, fluctuations in temperature of roughly 1 part in 100,000, blobs of around a degree dominating the structure. This is all the structure in the galaxy distribution waiting to be born. Today, we've got the data from the Planck satellite, and it's truly said that this is one of the best agreements in all of physics between a priori prediction and empirical determination. The basic cold dark matter model depended only on 5 physical parameters. You had to specify the amplitude and the slope of the initial fluctuation spectrum, the densities of the dark matter and the baryonic component, and the cosmological constant. And when you do that, you have a power spectrum of the temperature fluctuations with this nice peak at round about 1 degree scale that you saw on the WMAP map, and also perfect agreement with the polarization properties. We clearly understand something very well here. Lambda, so the key ingredient that's emerged out of all of this, was invented by Einstein in his first cosmological paper in 1917. Today we would use the term dark energy, and what it means is that empty space has some non-zero energy density. And this was concluded really even back in 1984, where these early calculations of microwave anisotropies in the cold dark matter model showed you that you couldn't have an extremely low density universe. Upper limits that existed at the time ruled that out. So you either had a high density matter dominated universe or a lower density matter universe with a residue made up by this uniform component. And for a long time we had plenty of evidence that the necessary high dark matter density couldn't emerge. So it was not considered surprising when, at the end of the 20th century, studies of supernovae measuring the distance redshift relation, which gives you the expansion history of the universe, also argued for a lambda-dominated model. So we've had, for 30 or 40 years, this standard lambda-dominated model of the universe as the default cosmology. And we just proceeded to test it. One of the strong tests came from large-scale structure. So the microwave background, the early fluctuations that you saw in the WMAP picture, should grow under gravity to make distributions of density in the universe today. We map these with galaxy redshift surveys. Here's an iconic picture that I was very proud to be associated with, the 2DF redshift survey. Every dot you see here is a galaxy like the Milky Way, shall we say 100 billion stars, and they're connected in these filamentary and void patterns. So here you're seeing, well, the scale goes out to redshift of 0.2, 20% of the way to the microwave background. And here's 1 billion light years. It's staggering to think that we exist right here as part of this whole network. One of the things that 2DF did was measure, as with the microwave background, we could measure the fluctuation spectrum, how the fluctuations in galaxy number density are spread out according to Fourier modes of different wavelength. And that's the data here, superimposed on a range of cold dark matter models, which have a variety of ratios of dark matter to baryon density. The ones here have large fractional baryon density, and you see oscillations. Those are the so-called baryon acoustic oscillations, representing the fact that sound waves can propagate in ordinary baryonic material, unlike in dark matter, which is collisionless. And you see the data have very weak baryon wiggles. This was the first detection of that phenomenon in 2001. And that is really direct proof that the dark matter exists and is collisionless. Okay, so all this is working very well, and yet the media are full of stories like this, that everything in this standard picture is wrong. So what's caused this controversy? I'll focus on 2 issues. One is the Hubble constant tension. So H0, the Hubble constant, is the rate of expansion of the universe. And that's a parameter that comes out very accurately from fitting the CDM model to data like the microwave background. You get a value of about 67 kilometers a second per megaparsec. But people who've tried to measure this directly using Cepheid variable stars and supernovae as distance indicators get a result that's about 10% higher. So is there some piece of missing physics in the standard model that bridges this gap? That's one tension. Another tension that receives a lot of emphasis in the literature relates to results from gravitational lensing. So gravitational lensing is a fantastic phenomenon for making pretty pictures. Here's a splendid one from the James Webb Telescope. In general, massive foreground galaxies, like these red ones here, can take blue background galaxies and distort their images substantially. This is very rare to have this level of gravitational lensing, but typically, if you just look at a galaxy at a random direction in the sky, its ellipticity will have been altered by about 1% by effects like this. And this can be measured statistically to high accuracy. Gravitational lensing also impacts on the microwave background. So when we look at the WMAP picture, we're actually seeing it. You know, they need to make the laser button a different color from the forward button. So there's the microwave background, and we're seeing it through all the large-scale structure, the dark matter fluctuations that we've traced with the galaxy distribution along the line of sight. And so there are subtle distortions in the microwave background. Amazingly, you can use those, and the way it's done technically is that the microwave background to high approximation is what we call a Gaussian random field. So its harmonic decomposition is a set of modes entirely of random phases. But the correlation, the deviation of light by gravitational lensing introduces some phase correlations, non-Gaussian features. And those allow us to make a map of the structure that's along the line of sight to the microwave background. So the first map that I showed you from the CMB was just the temperature fluctuations, 1 part in 100,000. But this is analyzing that to try to pull out the non-Gaussian signature. And so you see hot and cold spots. And these represent every supercluster that ever existed in the history of the universe, somewhere along the line of sight. Excess dark matter, deficiency of dark matter. And these are all real structures. The problem is that you don't get a direct measure of the distance to these structures. So how do you learn something from their apparent amplitude? The answer is you can do this by cross-correlation. So here's more examples of mapping fluctuations in the galaxy density field. So what we have here is relatively thick slices, redshift 0 to 0.3, going up to redshift 0.8, and it's color-coded with the fluctuations in the galaxy number density, roughly up or down tens of percents in numbers. And I think you can see that this is the more distant shell. The closest shell to us, the structure is of larger angular size. So we can cross-correlate these slices with the CMB lensing map and pull out the fraction of the lensing structure that lies at low redshift and measure its amplitude. When you do that, what you get are results that are low compared to the standard model prediction. So this is characterized here. So there's a parameter sigma 8, which just represents the amplitude of density fluctuations today. This is the density parameter in matter. And these different bands show the locus on that plane that accounts for the amplitude of gravitational lensing, either seen in purple, the amplitudes of the weak ellipticities of galaxy images, or in red, the cross-correlation analysis with CMB lensing. The consensus of these measurements is somewhere to the left of this green blob, which is the standard model as inferred from the microwave background, the Planck parameters. Now it seems that the natural way of accounting for this is to say that you want the density of the universe to be rather lower than Planck prefers by several standard deviations. So Planck's fiducial density parameter is a little over 0.3, 0.315. the lensing analyses prefer about 2.275. So again, has something gone wrong with the standard model? Is the theory of gravity incorrect? Have density fluctuations grown at a level that we wouldn't predict? Well, we need some more opinions. And the baryon oscillations that I showed you in the power spectrum of matter fluctuations are an extremely clean and powerful way of doing this. Okay. So a little more about the baryon oscillations. They're a causal process. They represent the impact of gas pressure on matter in the universe. And so they can redistribute matter, but only on a scale within which causal signals can propagate. So there's a key length, which is the acoustic horizon. That is the distance that sound waves can propagate over the entire history of the universe, which is actually of order of magnitude the causal horizon, just speed of light times time. And we see this horizon, for example, in the power spectrum of the microwave background. Here it is again, this peak at angular scales of about 1 degree. That's saying that the length that sound waves can have propagated by the time that the microwave background photons are scattered subtends an angle of 1 degree. So that information, what we actually have available to us is a standard ruler. I suppose there's a ruler back there, but you know what a ruler looks like. Something of standard length, which you can either look at close to you, which subtends a large angle, or take it further away when it looks smaller. Good. So that allows us to study this signature potentially at different redshifts, not in the CMB, because that's only at one location, but in the galaxy distribution. We showed the 2DF results, which with larger samples become much higher signal to noise. In the power spectrum, it's a series of oscillations. In the autocorrelation function of the galaxy distribution, it's a peak of excess pairs of galaxies separated by about 100 megaparsecs. So this BAO signature has been big business in cosmology of late. And the experiment that's pursued it with the greatest success is called DESI, the Dark Energy Spectroscopic Instrument. And this is a repurposing of the Kitt Peak 4-meter telescope, which has been taken over entirely with a fiber optic spectrograph that can measure 5,000 galaxy spectra simultaneously. And it's been dedicated to this experiment for over a 5-year period. So in that time, we've been able to measure something like 30 million redshifts, which is 100 times the data volume of the 2DF survey that I showed you earlier. And here's an illustration of the progress. So this is a 250,000 redshifts from 2DF. The bright galaxy subset of DESI, the faint galaxy subset, which goes out to redshift 1, and there's quasars, which would require an even larger projection screen. So we're able to measure the density fluctuations over a much larger volume with hugely better statistics than was ever possible before. And this is the paper that caused a lot of the headlines. It was first posted in March of this year. So what we're able to do is, over a redshift range between about 0.3 right out with the quasars to beyond redshift 2, is to measure with high precision this baryon acoustic scale, the scale at which it appears to exist, that is, the angle it subtends, as seen from our location. And so we've got the distance redshift relation over this entire span, and we can compare it with the one that would be predicted from the standard cosmological model as read off from the microwave background. And that's what you've got here in a ratio form. So it's actually upside down to how I would have preferred to plot it, because it's the it is, I would have wanted to plot the angle subtended by the acoustic scale divided by the prediction, but it's actually the inverse of that. Anyway, it doesn't matter. The point is this dashed line here represents the apparent size of the acoustic horizon as it should have been according to the Planck model with a high density, and here are the measured values, which are clearly discrepant. So the preferred density that comes out of this is about just a little under 0.3, as opposed to the Planck 0.315. So again, as with the lensing, we've got a discrepancy in terms of the density of the universe. Okay, but to complicate the story still further, if you try to do the same analysis with supernovae, which are not standard measuring rods, but are standard candles, type 1a supernovae can be processed to be objects which we expect to be of uniform luminosity. And so looking at their apparent magnitudes as a function of distance should enable you to plot out the distance redshift relation. That prefers a higher density universe. So you've got the microwave background, you have lensing, and BEO want a lower density, supernovae want a higher density. How can we reconcile these 5 different things? Well, this is visually what you want. So again, here is a plot that's a ratio of distances or a ratio of angles. Straightforward, the horizontal line would be the Planck prediction. These colored points are the DESI results. These solid points are results from supernovae. So just changing the density of the universe to the lower DESI value would produce this monotonically descending blue curve. But apparently with a supernovae in the picture, you want something that has this dip. What does that produce physically? How much longer do I have, by the way? Oh, don't worry. No, the chairman should be very accurately on it. The model that accounts for all of this is evolving dark energy, and this is the thing that you've heard of in the literature. Cutting out the technicalities, it's this. You need a density of dark energy which has a non-monotonic behavior. So relative to its value today, rather than being a cosmological constant at 1, it goes up by 20%, peaks at a redshift of around 0.4, and then falls at higher redshift. If you read the literature at all, you will come across this characterized in terms of this equation of state parameter, the pressure of the dark energy divided by its energy density, which for a cosmological constant would be -1. And what we do is take a simple Taylor series model in which this equation of state slides uniformly with some present value and some evolution according to the cosmic scale factor. And you see the preferred model fit is away from 0 evolution and -1. So theoretically, this has stimulated a lot of papers pointing out how hard it is to explain this. But at the time, I have to say I was quite impressed. You have many diverse data sets that all naturally fell together if you allowed the dark energy to have this evolution. And I have to say, I was a late adopter of the cosmological constant. I thought it seemed very unnatural to agree the vacuum could have energy. So I tried this time to abandon my skepticism and accept that it could also evolve. And if we were giving this talk in April, that's where it would finish. We'd be saying, this is so exciting. We used to think we just had this one number, the cosmological constant. Now we have an entire function of time, its energy density, to measure. So the subject has become rich. We need new experiments. We can plan for the future. Okay, but since then, 2 worrying papers have come out. The first suggests that there are systematics in the calibration of the supernovae. Well, at least not of the supernovae themselves, but to understand the supernova light curves, you need to understand a very basic thing, which is the transmission curve of the filters that you use to observe. So if you don't know the transmission of the telescope as a function of wavelength, you can systematically get the supernova magnitude wrong as a function of redshift. That's called a K-correction error. And the suggestion is that that's exactly what happened with the supernovae, and that they should be shifted by 3% in flux at redshifts getting on for 1 compared to the present. That doesn't sound like very much. That's pretty high precision calibration. But it's enough, as it turns out, to change the density from the preferred value from the supernovae alone of about 0.35 to about 0.3, the same figure as gravitational lensing wanted. Okay, you still have the microwave background not holding out and wanting this higher density. But here's a very nice paper pointing out that the density that we get from the microwave background depends on an astrophysical parameter, which is the effect of reionization. The universe around us today is completely ionized. That became so at redshift of 7 or so as a result of early star formation in the high redshift galaxies. We see this polarization of the microwave background from scattering of this local ionized plasma. And that allows us to measure an optical depth through Thomson scattering of that local material. The conventional figure for that is about 5%. And the evidence for it is here. There are 2 plots which represent the polarization data, one directly, the other in cross-correlation with the temperature. There's the 5% curve, which you can see is in very poor agreement with the cross-correlation data, fine with the direct data. If you raise that to 7%, it doesn't look like you could really argue to me that that's ruled out, given the likelihood of systematics here. The implication is huge, because the higher the optical depth is, the lower the preferred density. This is quite reasonable, that if the optical depth is high, it means the actual amplitude of fluctuations is higher than you thought. Therefore, gravitational lensing should go up. But to make the signal as it's observed, you would have to lower the density of the universe to reduce the signal. So it's inevitable these are anti-correlated. So we can hit this lower density if we just assume that the optical depth from reionization is a bit larger than Planck quoted. And given the systematic looking signals I'm seeing at these few large angle multipoles here, it wouldn't surprise me if that was the case. And if you accept all this, that the universe has a lower density than Planck first thought, the Hubble tension largely falls into place. The microwave background tends to measure this degenerate combination from the acoustic scale. So if you lower the density, the Hubble constant has to go up. And we can get close to the direct measurements just by assuming that the density is lower. So there we are. We've had this standard model. We looked as though earlier this year we were headed for a revolutionary change. Finally, after 40 years, a new cosmology. It now seems much more likely to me that we were fooled by small systematics in 2 of the key data sets. That's a very concerning situation to be in for the future of the subject, because even if now we say, for the present, it looks like the lambda CDM standard cosmology with a slightly lower density is a good default for everything we currently know about. Given that we've been fooled by systematics once, how are we ever going to convince ourselves or the wider world that any future claims of deviation from the model are to be believed? That's not necessarily such a disaster, because there are many interesting things still to do. If we think that the cosmological model empirically has actually come to an end, we know what it is we have to explain, we still haven't begun to explain physically what dark matter and dark energy actually are. But it's interesting that in a single human lifetime, maybe we've reached the point where the target for these physical investigations is not going to change. Thank you very much.
Thank you very much for the fantastic talk. So we have time for 2 questions.
Professor Peacock, thanks for your presentation. And I also would like to thank for your many textbooks. I learned cosmology from your physical cosmology book.
There's only one as far as I know. But
And I also
maybe I'm missing some royalties.
and I also use that kind of textbook to teach my students as well. My question is, there are 2 questions. The first one is if you believe that the current data shows some hints beyond the lambda CDM model, then what kind of model do you prefer personally?
Well, I tried to make my position clear in this talk. I think there's no evidence at all now for deviations from cosmological constant as the dark energy. It would be very interesting, if we finally convinced ourselves there were small deviations. The form of those deviations, well, I'm not going to tell the universe what to do. We'll wait for the data to speak. But at the moment, the danger is, I think, the theorists have been very keen on looking for deviations, and the observers maybe were too keen to supply those.
And my second question is, do you have any comments for the current investigations for 21 centimeter for cosmology? Thanks.
Well, yeah. I mean, 21 centimeter cosmology is very interesting because it allows us to do a direct probe of this key era for reionization. So I think my view is that there are a lot of areas of cosmology that you would say are not truly fundamental. That is, they don't bear on how much dark matter there is, processes deriving from the earliest inflationary theories and so on. They're purely astrophysical. So we've learned a lot from James Webb about the progress of the reionization process in the universe. And so actually mapping that directly, seeing the ionized bubbles around early galaxies, that in redshifted 21 centimeter, that'll be fantastic. But whether it will add to the kind of robust, clean information we need for testing the fundamental model, I doubt.
Go ahead.
How much does the DESI team accept that their calibration and so on wasn't perfect?
Well, okay, I am a DESI team member, and I signed that March paper. I'm not speaking on behalf of anybody except myself today. I mean, DESI, as far as I see no evidence for any systematics in the DESI data, so it's arguable it's possibly the cleanest of all of these things. I mean, you can ask whether the supernova cosmology teams themselves accept the reality of this suggested miscalibration. Now, I know the Dark Energy Survey supernova team are working on a paper either incorporating or attempting to rebut these suggestions. In a way, it doesn't matter which conclusion they reach. It's just, as already emphasized, that everything that we conclude is so sensitive to things that we haven't measured as well as we ought to, like filter transmission curves. That should serve as a warning.
Thank you.
Right, let's thank Professor John Peacock again. It's my pleasure to welcome our next speaker, Michael Perryman, who will tell us about the revolution going on in the Gaia mission. Let's welcome Professor Perryman.
Well, good afternoon, everybody. I'm Michael Perryman. My career has been with the European Space Agency, where for 17 years I was the chief scientist for the Hipparcos project, and then a co-originator with Lennart Lindegren of Gaia, and Gaia's chief scientist for the next 15 years. Gaia was launched in 2013. It was operated for 10 years until earlier this year, 2025. This is what the telescope itself looks like. It's a large 3-meter, 4-meter diameter silicon carbide torus with 2 mirrors, one of which is mounted here. I'm not going to go through any of the details about how Gaia makes its measurements. The details are complicated, involved, and took a lot of people a lot of time to figure out. It's a large satellite. It was launched with the solar panels folded up against the telescope structure for launch. It was positioned out at the L2 orbit, so 1.5 million kilometers from the Earth, and it sat there for 10 years in this equilibrium, unstable equilibrium location, scanning the sky and measuring the positions of the stars. Now, the details are extremely complex. Controlling the systematic errors, which is all what Gaia is about, enters into many, many details. But the principles are very, very simple. And let me explain that. It's simply the effect of parallax, which you're aware of if you hold one finger up, close one eye, close the other eye, and the finger appears to move. It's not actually moving, but it appears to move with respect to the background. And exactly the same is true as the Earth goes in its orbit around the Sun. One of the consequences of Copernicanism is that the nearby stars should appear to move with respect to the background stars. And that is the principle on which Gaia and Hipparcos before it are based. On a rather complicated figure of accuracy versus time, what I'm plotting here is the angular accuracy in positional measurements on a logarithmic scale. And here we've got time running from 400 or 500 years ago to the present date. And you can see that over the last 400 or 500 years of recorded history, the accuracy improved with time in a logarithmic form. And that was broken by Hipparcos and indeed by Gaia with the opportunity of going above the Earth's atmosphere. So the ability to get beyond the phase-perturbing atmosphere, which Reinhard Genzel just displayed with his laser guide stars from the ground, is immediately obviated if you can go above the atmosphere. And there you are no longer affected by the phase perturbations of the troposphere, and you can get diffraction-limited imaging from your telescope. And what we did with Hipparcos was to drop down to about 1,000th of an arc second, and with Gaia, accuracies of around 10 microarc seconds, so systematic errors below around 1 microarc second, or in the language of atomic physics, equivalent to the radius of the classical electron radius at a distance of about 10 meters. So what that has enabled is the possibility of observing a very significant fraction of the stellar content of our galaxy and determining the distances for the first time, and indeed how the stars move through space. So distances of stars are astronomical. If we took the Earth's population of 8 billion people and separated them by 5,000 kilometers, that would take you to the nearest star at about 1 light year. And of course, the galactic center is considerably further, about 8,000 parsecs, 8 kiloparsecs, 30,000 light years. And we're out somewhere in one of the spiral arms. Now, when Hipparcos, the first satellite dedicated to astrometric measurements from space, Hipparcos, was launched and the catalogue came out in 1997. It was a catalogue of 120,000 stars, which we thought at the time was pretty revolutionary, and it was published in 5 printed volumes. This was in an era, even in 1997, where we weren't confident of the long-term duration of things like the World Wide Web or whatever, and the catalogue was printed in 5 volumes. If you were to print the Gaia catalogue in exactly the same format, with just the primary data from Gaia, the positions, the parallaxes, and so on, it would occupy 10 kilometers of shelf space. So it really is a revolution in numerical terms. And what I'm going to do today, without saying anything more about how the measurements are done in detail, just give you a few examples of some of the scientific applications that are being used with Gaia. So I'm going to show most of these little animations are fields of view about 40 degrees by 60 degrees. You will recognize some of the star fields. I've used a slightly different transformation of linear magnitudes versus star sizes to accentuate some of these. But as I go on, I'll point out that these are animations that are based on real data. They're not simulations. They are using the Gaia data to demonstrate how the stars are actually moving through space. So I'm going to start off with, I need some of my notes here for distances, but this is the Ursa Major, one of the 48 constellations listed by Ptolemy 2,000 years ago. And you probably know quite well that if you put time going forward, you can see that this constellation that is well recognizable today looks very, very different in 100,000 years from now. So that is one example, just using the Gaia data to demonstrate how the constellations will look in 100,000 years from now. If I move across the sky, I'm going to center the next animation on Orion's belt, Alnitak, Alnitam, Mintaka, stars at around 80 light years. And what I'm going to show in this next animation is how the principle of parallax works. What I'm showing there is on an expanded, accentuated form is how these nearby stars would appear to move with respect to the distant stars. Now, of course, that's multiplied many, many times to get that effect. But what you saw in that animation was the 1 year effective motion of the Earth going around the sun and how the nearby stars would appear to move with respect to the distant stars. Now, we can also measure how the stars are moving through space. If these measurements are made extremely accurately, we can actually see how the stars move across the sky. And again, this is enormously magnified, multiplied to get the effect visible, but the motions that you saw there are correlated, they are linearly related to the real measurements. And then the combination of the two, so you take the parallaxes, the apparent motion as the Earth moves around the sun, combined with the real motion of the star through space, and you can see that the stars then move one with respect to another in what appears to be a very complicated manner, but is actually only determined by 5 numerical parameters: the position in the 2 coordinates, the proper motion in 2 coordinates, and the distance of the star itself. And the principle of Gaia then is to make a repeated set of measurements over many years and to be able to disentangle those, to disentangle the position at any one epoch with the parallaxes and with the proper motions. What I will show now is just a couple of examples of this. So Aldebaran was one of the first stars whose motions across the sky was measured by Edmund Halley back in 1718. Aldebaran, Arcturus, and Sirius, I think, were the first measured proper motions, the first indications that the stars were moving through space. And if we run this animation forward in time, I'm going to propagate this forward, I think, 100,000 years. And you can see that Aldebaran is moving down to the south there. You've got Castor and Pollux, Gemini. And in the center of this field, I don't know whether you noticed, but stars moving systematically right to left. And this was the Hyades cluster. So Aldebaran is actually superimposed on the Hyades at the present time, but you see a cluster of stars that are moving through space. And this is the Hyades cluster, distance of about 40 parsecs or 120 light years, a key measurement point in the understanding of the distance scale in astronomy up until about 30 or 40 years ago. With Gaia, several hundred other stars have been identified as members of the Hyades cluster, and what we see there is stars escaping from the cluster into the tidal field of the galaxy. Something like 1,000 clusters, open clusters, were known pre-Gaia. Gaia has shown that a lot of those are not real, but there's something like 10,000 or so other open clusters that have been identified since then by Gaia through a combination of distances and proper motions. And they are fundamental in understanding stellar evolution, stellar structure, and so on. They are yardsticks in that. Just a little bit further north, northwest, is the Pleiades cluster, and I'm going to zoom in. The Pleiades, the Seven Sisters, and again, it's a system of stars which are gravitationally bound and will remain more or less in the same configuration, moving backwards and forwards within the overall gravitational potential, but remaining bound over over the next 100 million years or thereabouts. I'm going to move across the sky to Barnard's star. It's one of the fastest moving stars known, discovered by Edward Barnard in 1916. And again, setting the stars in motion, you will see there Barnard's star hopefully moving through space. Notice everything flickering here. These are the Cepheids and our Lyrae stars predominantly that are captured at different phases of their light formation by Gaia in its photometry, as well as the velocity of the star through space through its astrometry. Now, Barnard's star is, in a sense, I shouldn't say it's not a particularly interesting star. All stars are interesting. Some stars are more interesting than others. But Barnard's star is moving through space, or appears to be moving through space, simply because it's very nearby. It's a distance of about 6 light years. It's not moving rapidly through space because of any particular unusual space velocity. But we do see those, and I'm going to move now to another target. This is a star which I've labeled here as Hipparcos Catalogue 89825, but it's better known as Gliese 710. And one of the things that people started looking at with the Gaia data was to see which stars are going to pass close to our own solar system in the years to come, or which stars pass close to the solar system in the geologically recent past. Now, space is not only very large, but it's also very empty, and you would have to wait for many times the age of the universe for any two stars in the solar neighborhood to collide. But stars do come very close to each other, nevertheless, and as I propagate this forward, I'm going to propagate this star forward in time, and watch carefully, because Gliese 710 is approaching us, and in about 1.5 million years from now, it will pass by at a couple of parsecs, less than a couple of parsecs. And this is a field of study now being investigated to see whether close stellar passages in the distant past, in the geologically distant past, have been responsible for things like the perturbation of the Oort cloud and perhaps an enhancement in meteoric activity on the Earth, perhaps which created some of the mass extinctions in the past. So that's a field, stellar flybys, Oort cloud perturbation and so on, that has been very much opened up by the Gaia studies. The next star on my list is known as Gaia BH1. It's the first of the stellar black hole discoveries in the Gaia dataset. Gaia is discovering this from the tiny wobbling motion, because if you measure the star repeatedly, you see these stars moving backwards and forwards. Binary stars they come in a huge variety, and we can zoom into Gaia BH1 and do a little tour around Gaia BH1. We don't see, of course, the stellar black hole itself. You see this particular black hole is considered to be in orbit around a main sequence star, and you see that main sequence star actually in its reflex motion around the common barycenter. So this is now Gaia BH1 is a Gaia discovery, discovered in 2022. It's 480 parsecs away. It's a black hole that's inferred to be about 10 times the mass of the Sun in a 185-day orbit, and several of these are now becoming unearthed by the Gaia data. I'm going to switch to another topic, which is runaway stars. Now, stars in the solar neighborhood move through space with respect to the rotational velocity of stars around the galactic center, with a velocity standard deviation, standard error of something, a motion, a random motion of order 10, 20 kilometers per second. Now, about 60 years ago, was discovered the first stars that were moving at much higher velocities, 50 kilometers a second, 60 kilometers a second, and these are termed runaway stars, and they're stars which are known to now be running away from their birth cluster. This, again, is quite a large industry in stellar astronomy, looking at the origin of these stars. This is, I showed it there, UW Ari or 53 Ari, and I can navigate in. Unfortunately, you've seen all of these with, what was it called, not Star Trek or whatever. You've seen those kind of animations, but this is real data. That's the important point, I think, to stress in this. So this is 53 Ari, and it's moving away from its birth cluster with a velocity of about 60 kilometers per second. And again, there are a number of theories about why these runaway stars originated, either from a binary supernova explosion or dynamical encounters with other stars in the birth cluster. Now, nature is even more extreme, and in 1988, there was predicted to be a class of star called hypervelocity stars. And these were predicted in 1988. The first one was discovered in 2005, and Gaia is discovering many more. These are stars which are moving at much, much higher velocities, of order 1,000 kilometers per second up to 1,500 kilometers per second. 1,500 kilometers per second is 0.5% of the speed of light. These are 10 solar mass objects moving at of order 1% of the speed of light. And this is Lamos HVS1. It's the, sorry, I'm going to move across the sky to Lamos HVS1. And it's the brightest of the known hypervelocity stars. And the theory back in 1988, confirmed experimentally, is that what you're seeing here is systems, binary systems, which have been disrupted by very close passage of the supermassive black hole at the center of the galaxy. What this does is tidally disrupt the binary and ejects one of them like a slingshot, and it shoots off at high velocity through space. Lamos HVS1 is a distance of about 160,000 light years. As I said, traveling at about 1% of the speed of light, it will still take tens of millions of years to escape the gravitational confines of the galaxy. Another very nearby star is Groombridge 1830. It doesn't move quite as fast as Barnard's star, discovered by Stephen Groombridge in the early 1800s. It's again very nearby, and it has a particular interest that it's moving very rapidly. It not only appears to be moving very rapidly through across the sky, but it's also moving very rapidly through space, and it's a member of the halo population. So we, the sun, are sitting in the galaxy disk. Around us are the halo stars sitting in the dark matter halo, and if some of those come close to the sun, they move past and fly past at a very high velocity, space velocity, and Groombridge 1830 is one of those. I've just got two more examples. One is connects a little bit to John's previous presentation about what kind of disrupts are going on in cosmology. And this is a star called HD 140283, and it's better known as Methuselah. And although we seem to have a very good understanding of the age of the universe, 13.8 billion years plus or minus, this has been measured at an age of 14.5. Most recent measurement made by the Hubble Space Telescope, published about 5 years ago, and they list its age as 14.5 billion years. Now, there won't be anyone in the audience who would not just laugh that off and say, well, there's something wrong with stellar evolution, and that is almost certainly the case. But at the moment, that is an unresolved, and there are several unresolved, very, very old stars which appear to push in conflict with the empirical age of the universe. I think the surprising thing is not that these stars exist, but that the majority of stars fit beautifully consistently with any understanding that we have of the age of the universe. My final example, I'm just going to show that. Am I? No, I'm not. My final example is Arcturus. It was one of the other, the three stars identified by Edmund Halley in 1718 as showing proper motion. And Arcturus is very nearby. It's about 30 light years, 11 parsecs, and it's moving at about 100 kilometers per second. Arcturus was one of the stars studied by Olin Eggen, an eminent observational astronomer who pointed out several moving groups and curious structures in stellar groups moving through space. And he's been vindicated by this one because Arcturus is now known to be a member of the Arcturus moving group. And in particular, it's part of one of the halo streams that you may have heard about, the streams of stars that have been captured by cannibalized galaxies, by our more massive galaxy. And I show that in this very simple simulation, which may work, and it may not. But the stars are disrupted as the cannibalized galaxy is captured by our own galaxy. These stars are torn off and reside in the outer reaches of our halo as these stellar streams, which are direct sort of archaeological evidence of the formation of our own galaxy. And I will show, again, just for completeness there, one of the simulations that comes through these large-scale numerical cosmological simulations of formation of structure in the universe. This is, again, that one doesn't seem to... Oh, well. What we see from these large-scale numerical simulations is structure that very well replicates the sort of structure that we're seeing with Gaia. The large-scale motions of stars around the galactic center, but also perturbations due to cannibalized galaxies or local disruptors or whatever. So I think that was my very brief introduction to Gaia. When I've shown you these star fields, just bear in mind that I picked out something like a few hundred of the brightest stars. In a typical Gaia field of this size, there are about 200 million stars. So a great database for many, many investigations that are going on. There's something of order 8,000 refereed scientific papers that have appeared so far based on Gaia, spanning many, many different areas of astronomy, which I tried to give you a flavor today. Thank you very much.
So we have some time for questions.
I just have a simple question. Did Gaia try to detect exoplanets?
Have you not read any of my papers? Yes, indeed. And It's a very interesting question. Thank you very much. At the moment, there are something like 5 exoplanets that have been published from the Gaia data, 2 from photometry, so from the photometric transit signature, and 2 or 3 from astrometry. My own predictions are that we'll see about 50,000 planets from Gaia. So they will wait probably until DR5, so the final data results. At the moment, we've had 3 data releases. DR3 was the most recent, and DR3 used the first 3 years of data from Gaia. There are 10 years of data in total, and as the data quantity increases, as the time period coverage increases, and as the calibration improves, then I think we will see an ability to detect large numbers of exoplanets from their astrometric motion. And these will be interesting because they will be primarily a sort of Jupiter-like planet in a Jupiter-like orbit. So very much unlike the planets discovered by Kepler or TESS or whatever, which are close-in planets, these will be planets much more like the solar system. But I think in the next few years, we should see several thousand planets coming from the Gaia database.
I see. Thank you.
Professor, thank you so much for your very exciting and interactive presentation. Really enjoyed it. Yeah. So I just have a quick question. So what blind spots do you think the Gaia community is collectively underestimating today? Is it sampling, velocity systematics, or astrophysical priors?
I'm not quite sure I understand your question. Are you asking in a way where one can do better in the future, or?
Yeah, essentially.
Perhaps this is one point that I should stress, in fact, and it's one of the reasons that one comes and gives a presentation like this to a community like this. The achievements of Gaia, I think, are extraordinary in terms of accuracy and numbers of stars. What you can see, though, is there is no immediate limit to the accuracy that one can achieve in optical astrometry from space. You should certainly be able to get down to sub-micro-arc seconds. My own investigation sort of suggested that the floor of accuracy only comes in at something like 10 nano-arc seconds, where things like interplanetary scintillation or stochastic gravitational wave background come in. You can go down much, much higher. Now, Gaia isn't equipped to do that, so it's a question for the next generation to figure out how you build a satellite with a bigger collecting area, a better control of accuracies, and so on. I'm not sure at the moment that I would say Gaia has got any real blind spots. What we will see in the next few years is, can we calibrate Gaia with the precision that's actually needed to get down to the kind of ultimate accuracies that the instrument is capable of? And I think that remains to be seen. Part of that will come down to, are the funding authorities willing to continue to fund the data processing effort on the ground in order to go through those iterations that will be necessary to do that. So maybe calibration is one problem. Which still to some extent limited by computational power. What is going on at the moment, the preparations for DR4. DR4 will be 6 years of data, and DR4 has been iterating at the main computer center in ISAC in Madrid for the last year and a half, and it will be iterating for the next 1 year until convergence. So to some extent, we're limited by computational power. It's a huge numerical processing task. So will the funding authorities be willing to, to continue to investigate photometric, chromatic terms, instrumental terms? That may be one limiting factor.
There was so I think I agree with you that Gaia has been revolutionary, and it's amazing that this and Hipparchus, its predecessor, basically has made a revolution in an area which a large fraction of astronomers thought was dead before this came. And you're only able to touch on a few of the areas. So one which particularly intrigued me, and I'd be interested in your opinion on, is quite recently Gaia found several black holes of quite high mass by tracking stars and seeing when the proper motion track was not really a straight line, but had wiggles reflecting an orbit around another object. And these turned out to be orbiting an unseen black hole, and some of the masses came out to be quite surprising. So this was still in some of the earlier data releases. So my question is, how many more such objects can we expect or hope to see in the new data releases?
I mentioned that, Simon, with Gaia BH1. That was one example, exactly as you say, where the proper motion track is perturbed by some unseen companion. And I think there are 3 at the moment that have been published. They're of order 10 solar masses, the black holes. I can't, in all honesty, answer your question, how many will come out. What will happen is the next data release, DR4, it will have so much more data, so many more data points, that the orbital coverage will be vastly better. And DR5, when it comes out in 2030, using all 10 years of data, again, will be some orders of magnitude more powerful in terms of binary orbit classification. So if I were to pull a number out of the air, I would say certainly of the order of hundreds. But
great. Thank you very much.
Pardon?
I think you can do 1,000.
Well, there you are.
So there's one more question at the back, quick one.
Yeah. Question because of the sheer volume of data coming out of Gaia and how long Gaia was in preparation. I was very curious to know what impact, if any, on the data analysis has the AI revolution had, or whether you can comment on any developments that are planned in the future.
Yeah, thank you. It's not an area that I've been following in detail myself. The AI is more relevant in terms of classification. It's not relevant, it has not been relevant, and I think will not be relevant in the iterative solution. The basic problem that has to be tackled is that you've got, so far, 1.8 billion stars have come out in data release 3. There will be closer to 3 billion stars in data release 5. That number is dwarfed by the number of attitude unknowns and calibration unknowns, and they all have to be solved in a very big iterative process, and that has to be controlled in the cyclic form of the convergence. And that is something that will not be improved by AI. Where AI is having, I think, a huge impact already is in the classification. So you're seeing that many papers coming out with improved classifications on metallicity, temperature, the fundamental properties of stars. I should mention that Gaia is not only delivering these positions and proper motions and binary parameters and photometric parameters, but they are being input to stellar models which are spitting out, again, to the best of our understanding of stellar evolutionary models at the moment, masses, radii, temperatures, effective gravities, metallicities, interstellar absorption, and so on. And this is the area where machine learning is having already a very, very rapid contribution. Yeah, years ago, one of the first directors of ESO, Adrian Blau, when we were coming up with plans for Gaia, he said to me, he took me on one side and said, didn't I think that Gaia was a little bit too ambitious? Shouldn't there be some kind of intermediate step? Was the community really ready to actually process this amount of data? And I think what you see in so many areas of science, and I think that's a great lesson, is that things move rapidly in many sort of parallel forms, allowing these sort of obstacles to be overcome. But one of Gaia's great interests is not that you're measuring 3 billion stars, but you're measuring 3 billion stars out of which you can capture this particular very rapid phase of stellar evolution or whatever. Thank you.
All right. Well, let's thank Professor Michael Perryman again. nearing towards the end of the session, I'd like to thank the speakers again. And I'd also like to just take the opportunity to encourage all the young scientists to make use of the Hong Kong Laureate Forum. I think it's a very good opportunity to learn from world-renowned scientists. And for me, I've each time that we have the Hong Kong Laureate Forum, I'm astonished by all the achievements, and especially for many of the local students. I would strongly encourage you to take take the opportunity as much as you can. So thank you very much again to the speakers and to the audience for the very nice questions. And I'll hand it over to the MC.
Thank you very much, Professor Hannuksela, for hosting such inspiring sessions. Please be seated. And also a sincere thanks to Professor Balbus and Professor Peacock and Professor Perryman for the insightful presentations. Please give a round of big applause to show our huge appreciation to the professors. Thank you very much. And time flies. We have come to the end of this session, and we hope that you have gained some new knowledge, which I already heard, and some insights from our speakers. Please do take your time to exchange further and network with each other around you. For our honorable laureates and forum participants who have enrolled for the next agenda, Victoria Harbour Tour, and a welcome dinner at West Kowloon Cultural District, we have arranged coaches to transport everyone to the Central Pier for ferry boarding. Following the ferry ride, we will provide coach service to the dinner venue. Please follow our event staff outside the hall to the coach boarding area at Building 15W before 4:45 p.m. While the coaches are getting ready, please catch our staff outside the hall here, and then they will bring you to the coaching boarding area. For easy identification, the coaches will have the logo of the Hong Kong Laureate Forum shown. Once again, we'd like to express our gratitude to the speakers and moderator for your time. And also, we are so happy to have every one of you in this session. Have a wonderful evening. Goodbye.